We only have
The
6
first is
problem
brain.
sets left, so we should spin the wheel.
Yeah, come on.
I'm so stupid.
Boo
I
you!
thought that n plus 1, when you did like n squared and you added 1 to it, it would be.
Let's be clear, I can boo you, you can't change your birth. Okay, so you get something like this if you go absolute, yes?
I made a poor
Uh,
mistake.
What test did you use?
Ratio.
Ratio test. By ratio test, the limit as n goes to infinity.
Until you do like, until you think that n plus 1 squared is really n cubed.
Plus 1 squared to
That's where I made a mistake.
Because I missed the ratio test.
Will we have time to ask questions after this lesson?
Probably not.
So hard. Because I just
not-
I just have like one question that I really desperately need answered.
I can help.
Thank goodness we have 7th period, right?
I'm not here for 7 hours.
Yeah, we have to go to McKellips today for 7th hour.
Do I not
Yeah.
have this?
Yeah.
I'm not asking for it to not be due today. I just really want to understand the question and why it's supposed to be answered. I feel like it's everything.
Oh, do soccer?
I'll do my best. Okay, so it's absolute convergence, yes?
Yeah.
Do I then proceed on to do conditional convergence?
No.
We do not. They're exclusive of each other. Conditional convergence is if it's not absolutely converging and blah, 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 blah. Okay? So they're exclusive, do not continue. You're done. All right, here we go. This is a humdinger. This is like the day you learn how to, what a definition of a derivative is. When you learn u sub or the first derivative test, this is big.
So it's important.
It's important. Okay. Now then, the idea of the day that's supposed to go through the origin. Okay. Is how do you fit a transcendental function? I use the word ugly in here, but typically the math word would be the transcendental function. Transcendental functions are functions that can't be computed easily by taking powers of x, like non-algebraic functions. You can think of transcendental as non-algebraic. X squared obviously is an algebraic function. Square root of x is an algebraic function. Sine of x, transcendental. E to the x, transcendental. Natural log of x, transcendental. So they're harder to calculate, and it would be great if we could actually make them algebraic. Well, that's the idea. We touched on this a little bit before. I could fit a sine curve with a polynomial. A first degree would be a line. It would be a mediocre fit. A parabola would be a better fit. Cube would be a better fit. A fourth degree would be even better. As you add more and more powers, you can fit the sine curve wider and wider out, and better around the point of tangents, all right? The idea then is we're going to create a polynomial of infinite degree and trying to fit this curve better and better. Now we write this in ascending order. We start at a constant, x to the 0 if you like, and gradually work up in power. What really needs to be determined is the coefficients. The coefficients have to be just right in order for this to all hang together. Now, the coefficients, there's a pattern to them, which we'll discover, but they all come from starting with some basic ideas that you've already played with. Now, if I want to match sine of x with some function, I first have to choose, like I do a tangent line, I need to figure out, all right, where do I want it to fit well? I want to center it around something. That's called the center, and we're going to use x equals 0. It's a logical starting point. Now, first and foremost, our polynomial has to actually have that point on it. We want them to meet at the point of tangents, yeah? Now, if f of x, or the sine curve, I'm letting f of x equal sine, needs to equal p of x, or the polynomial curve at x equals 0, then that implies that sine of 0 has to equal p of 0. Which is to say that if I use this polynomial, a plus b times 0 plus c times 0 forever would have to be the case, and that implies that a is 0. All right. Now, that's great. With an a of 0, they'll have the same y-intercept, and they'll be right together at the point of tangents. Are we cool? Now, if we were doing a tangent line, I would want my equation to have the same slope at that point. If they have the same slope, they have the same derivative, which is to say that f prime at 0 needs to meet or match p prime at 0. Our polynomial has to have the same derivative at 0 as the sine curve does. Well, we know f prime at 0 is cosine 0. And p prime. Well, there again, we're going to be looking at this again. I should probably box that because we're going to be using that over and over again. What is p prime?
Prime is b.
B plus 2cx plus 3 dx squared plus 4e, that's bad form to use e, by the way, but I did, I don't know why. X cubed, dot, evaluated at x equals 0, right? Cosine of 0 on the left is 1. B we know is, or sorry, B we don't know, is something. And all the other terms at 0 are 1s. And so from that we can conclude that B is 1. And our polynomial as it stands now is 0 plus 1x plus don't know c, don't know d, etc. Now we're gradually going to find those coefficients, trying to match not just the points and the slope or the first derivative, but now we'll match the concavity. So the change in the slope matches, and will fit a little better. That would imply that f double at 0 is p double at 0. What is f double at 0? Negative sine of x at 0. And what is p double? Now here's p prime. I have it right here. So now let's take the derivative on that. 2c plus 6dx. I like 3 times 2 dx better. Plus 4 times 3 dx squared plus, what would the next one be, just for fun?
5 times 4 ex to the 4th.
I won't call it f, so let's call it g. I'll skip the g. X to the 3rd, right? At 0. The left side, what is sine of 0? 0. And the right side, 2c is what it is. And the next guy is 0's forever, right? And that implies then that c is 0. Are we cool? Right? Therefore, p of x, as it stands with what we found, is 0 plus 1x plus 0x squared plus don't know d still, don't know e still, etc. Down.
Yes.
Okay, moving on and then looking for patterns. Make the function have the same change in concavity. Change in concavity means the change in f double or f triple needs to match. F triple, what is f triple?
Negative cosine.
Negative cosine of x evaluated at 0. And what is p triple?
3 times 2
3 times 2 times
1
D
G. Under that.
plus 4 times 3 times 2 times
E times X.
EX to the first plus 5 times 4 times 3 G X to the second. That's 0.
What's the next one? 6 times 5 times 4 H.
It would be. Next time is 6 times 5 times 4. H X to the first, or to the third, excuse me. So the left side negative cosine of 0 is
It is
negative 1. And the right side is
D plus 0.
3 times 2 times D, or negative 1 over 6. Nope. Negative 1 over,
6.
nope. 3 times 2. Okay? Times 1, actually. I'm going to throw in the 1 there, because why not? All right? Now then, my polynomial, as it stands, is 0 plus 1x to the first plus 0x squared minus 1 over 3 times 2 times 1 x to the third, right? And then I don't know what e x to the fourth is, dot, dot, dot. Or maybe being smart pattern recognizers, you could probably tell me that e is probably going to be 0. And f, what will f be?
1x to the 5th of 5.
Will it be positive or negative? Let's start there. Positive, 1 over
5 factorial.
5 factorial x to the 5th. All right, now starting to view a pattern, we could say that p of x, leaving out the 0 terms, is 1x minus 1 over 3 factorial x cubed plus 1 over, what did you say it was going to be?
5 factorial.
5 factorial x to the 5th minus, what's the next one, just for fun? 7th, or x to the 7th over 7 factorial. Now, say we wrote a pattern to this called a general term. There are 4 different things varying. What's one of them? Let's start with the first thing varying, is the
X.
sign.
Cool.
The sign oscillates, and therefore we'll need negative 1 to a power. Now, we typically start these as n as the first power. Now, the question then is, should we use n or n plus 1? If n starts at 1, then wouldn't negative 1 to the 1 be negative? And that's bad. We want it to start positive. So it should be n plus 1. What's another thing that's varying?
The X's.
The x's exponent. The x's exponent. What's the pattern in the exponent?
Well, it adds 2.
It's odd. What's the formula for making odds?
2
2n plus 1 or 2n minus 1. Now, if we start at 1, then should it be 2n plus 1 or 2n minus 1? It would have to actually be minus 1. Right? Over, now if you won't reinvent the wheel, do you agree the exponent and the denominator are exactly the same? And so we just are going to do that same thing down there. Okay? Now this actually has a dot, dot, dot after that because it does go forever. It doesn't end at a general term. That's just a picture of any term down the line. It does need to have the dot, dot, dot after to show it's an infinite series. Now this is called a Taylor polynomial or a Maclaurin polynomial. We'll get to the vocabulary in a minute. Now, this was lots of fun, but that's not the usual process for finding a Taylor polynomial. Typically, you will do this by virtue of a formula. So let's do some what's called math analysis. Analysis of mathematics. So we're going to analyze what we just did there. All right? So forget sign, and let's talk here. We're trying to fit f of x with this polynomial function, right? Okay. So if the first thing we did is we needed to ensure that f at 0 is equal to p at 0. Now, f at 0 over here, I actually did sign at 0, but now f is just going to stay any old function, not sign, just whatever function I want to match. Okay? P at 0 would be a plus 0 plus 0 plus 0, so that implies a is no.
A is f at 0.
F at 0. Okay? And at that point, our polynomial is f at 0 plus don't know b yet, don't know c yet. With me? Are you with me?
with you?
Okay. Then we fit or match the slopes, which is to say f prime at 0 needed to match p prime at 0. Well, f prime at 0 is what it is. Now we're going general, so I don't know what f prime at 0 is. I'm just going to leave it f prime at 0. But on the right-hand side, if I take the derivative of p, it would be b plus 2cx plus 3dx squared plus so on,
0 plus
right?
0 plus 0.
At 0 would be just b. And so if b is f prime at 0, that means my polynomial is f at 0 plus f prime at 0 x to the first plus don't know c, don't know d, cha-cha. Are you with me? All right. The concavity match implies that f double at 0 needs to match p double at 0. Will f double is what it is. I'll leave it that way. Here's p prime. Now take the derivative on
It is 2c.
2c plus 3 times 2 dx to the first plus, might as well do one more. What's the next one in the sequence? Or series? 4 times 3 x to the second, and we're going to evaluate that. We want them to match specifically at 0, so we're going to evaluate that at 0. When we do that, it becomes 2c plus a bunch of zeros, and therefore c is f double at 0 over 2, or 2 times 1 if you like. Therefore, the polynomial is f at 0 plus f prime at 0x plus f double at 0 over 2 x squared plus still don't know d, etc. Cool? All right then. Yeah, I kind of, but I'm glad you were thinking. Sorry, I debated whether to put it on the bottom or not. I didn't want to spoil it, but most of you are oblivious anyway, so I didn't want to. So, what do you reckon? Actually, let's do one more because I do like to show. Factorial to me seems like a probability and accounting function, and yet it's a huge calculus function. One more. F triple at 0 has to equal p triple at 0, okay?
Yes.
What is p triple based on the derivative of this line here?
Maybe
3 times 2 times
1.
1 times 1. I like 1. That's good. 1. D plus
4 times 3 times 2.
4 times 3 times 2. E x to the first. So on. At 0. From that, we could get the d is f triple at 0 over 3 factorial in the interest of space, okay? All right then, the general way to find a polynomial is something like this. Now, fitting a series to a function is called a Taylor polynomial or series. It has a specific name. When you specifically want a Taylor centered around 0, they have a specific name for that. It's called the Maclaurin series. Maclaurin is a Taylor when using a center of 0. Now, the idea then for that Maclaurin, you'll use a lot of notations. You'll sometimes see it written as, this is nth degree Taylor or Maclaurin. This should be 0, sorry. Would you change that C to 0? I pasted it from the back and I didn't want to. You could call this the nth degree polynomial. You could call it the nth degree Maclaurin series. And it is, just like we said, it's a polynomial gradually getting bigger and bigger in power. Constant, x to the first, x to the second, x to the third, x to the fourth, and so on, where the coefficient is determined by two things. The derivative divided by the factorial, and the factorial comes from all those powers that came down over and over. You with me? If, for example, I said, what's the second degree Maclaurin, then this is the ending or greatest power at which you stop. Okay? And so, for example, the second degree would have how many terms to it? 3, assuming none of them are 0. F at 0 plus f double at 0, x squared over 2 factorial plus f triple at 0. Nope, I got the first degree. I'm stupid, sorry. F prime, x to the first over 1 factorial, f double, x squared over 2 factorial. And all this hinges on the derivatives existing. They can be 0, that's fine, like sine, we had 0 derivatives in there. But the derivatives have to exist. If you get a D and E for any of these, the whole thing breaks down, you can't do a Maclaurin on it, it's gone. Okay? So the derivatives must exist at all orders at which you're trying to find the Maclaurin. Let me go then to the back. I think we're on the back, yes? Is there a little bit of notes I didn't cover, or did I get it all?
No, you got it all.
Okay, so there are four Maclaurins you absolutely have to have down cold memorized in a couple weeks, 3 weeks or so. Right now, you just know one, and you definitely don't have it memorized. These are the other three: cosine, E, and 1 over 1 minus x. Would you then, do you feel like you could find the Maclaurin for cosine? You know what you're doing, or should we walk through one together? Okay, try it, and then we'll talk about it. Would you write? It's typical to write the first 4 terms and the general term. Okay? So write the first 4 terms in the general term. Please. You typically start at 0, by the way, in the starting index. I started at 1 for sine, but it's more common to start it at 0.
Wow, so we have to like get through it.
So you don't have to do all that left side. Go to the formula. Use the Taylor series formula. Okay. So you're not doing all that stuff we just did. I don't. No. Okay. So that's why I was right. Maybe we should do it together. Okay. So. Yeah. No, I don't want you. That was just. I didn't want to just put the theorem down and say, here it is. Learn it. I don't care if you don't know where it is. I want you to know where it came from. But you don't do that every time. So it's this. It goes something like this. The Maclaurin series is. This, the first thing you're going to find is f at 0, which is to say cosine of 0. Cosine of 0 is? Actually, we'll show this much work, but we won't probably even do this much. Cosine of 0 is 1 plus f prime at 0.
Negative sign.
Negative sign at 0, x to the first over 1 factorial, that then
0.
drops out.
6.
Okay, now on to the second we go. This is the second derivative. And therefore, negative cosine of 0, x squared over 2 factorial. Negative cosine of 0 is
Negative 1.
negative 1, x squared over 2 factorial. Now, you may or may not start to see a pattern. Maybe you can tell me the next one without doing all the derivatives. What is it?
0.
Negative or positive?
Plus.
Positive, x to the
I guess 4.
fourth over
I didn't even think the next term.
4 factorial. The next term, positive or negative? Negative x to the 6th over 6 factorial. Now put a plus, a dot, dot, dot to say I'm going down the line to any point in the future. And now let's write the general term. You try and write the general term, please. Let's assume starting at n equals 0. Ready? Okay. So where did you start? The alternating negative or the x to the power? Alternating negative. Negative 1 to the n or n plus 1? If we're starting at 0, which we are, I'm making you start at 0.
Oops.
Then it is to the n. Okay? X to the 2n over 2n. And does that 2n need to be in parentheses, or is it okay to write 2n factorial?
You should do that.
Got to be in parentheses, otherwise that's n factorial double. That's not what you want. All right. Are you with me? It is also common. This is called expanded form. It is also typical that you write this in sigma notation. Now, if you wrote the general term, then you're home free here. It's just the same thing. The general term, typically we let this go forever. Okay? Now notice here, I didn't use a subscript. Why is that? Because this is infinite. I'm just saying the infinite one. Now if they said the second degree, well then I would stop it at second degree. But if you're not stopping it, you're going forever, then it's just a close. Alright? Do you get the idea of what I'm looking for? E should be fine. This, you better be careful. On the derivatives, you better be careful. A lot going on there.
Really? No, I know. I just.
I love you, right?
This one's fun.
Okay. Ready?
This one feels easy.
It is the easiest one. Ready? So it is 1 plus x to the first over 1 factorial plus, oops, that's x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial generally
X to the n.
x to the n over n factorial. If you did this in sigma notation, you would start it at 0, and it is x to the n over n factorial. Write yourself a note of some interesting stuff here. Notice that when we did the Maclaurin for sine, all the powers were odd, because sine is an odd function. When we did cosine, all the powers were even, because it's an even function. What about e to the x? Is it even or odd? It is neither, so you're seeing all the powers there, all right? Is not even or odd. So, if I asked you to estimate e to the second, actually just e, what's e, roughly?
3.
E to the first is like this Maclaurin at 1. So e to the first is 1 plus 1 plus 1 over 2 factorial plus 1 over 6 plus 1 over 24. That right there, I could continue on, but that is how your calculator calculates e. It is here 2 plus 2.5 plus 2 and 4 6, or 2 and 2/3. 2 and what? 16, 17, 24. You're getting closer and closer. All right.
Where are you going? I wasn't sure.
If you would, try this one. Give me 2 reasons why you should be careful with the derivative. There's a negative inside, there's a chain rule, and there's an exponent of -1. The more, you need to know yourself. Now, if you're super good at keeping all that straight in your head, fine. But me, the more complicated it is, the more I am prone to say f is 1 minus x to the -1st. F, and therefore at 0 is this. Then f prime is -1, 1 minus x squared, -2nd times -1, or what do we got there? 2 times 1 minus x to the -2 at 0. See what I'm saying? When there's so much going on, I would suggest doing some derivatives off to the side in a really organized fashion, so that you don't make a mistake. I just can't keep those straight in the Taylor itself. Okay? So do those, continue until you see the pattern. It is, there's most definitely a pattern.
Oh yeah. I meant to say the opposite of integrated. Anti-integrated. What's an anti-integration?
How are we doing?
I'm still doing the derivatives.
Okay? Take your time. I'm sorry, I didn't mean to rush you. It does take a while. Should this be... Why is there a 2 there? That's not a 2. That should be a 1, shouldn't it?
They all have cost. What's up, Michael? Michael, dude. Oh no, I made a mistake. I just put the numbers wrong. I mean, it didn't change my integration because it's integrating what it should have been, but like derivating what it should have been. But I don't.
Just so we're clear, you will, in a Maclaurin series, take higher order derivatives. Don't be that wiener that finds the 8th degree derivative and calls it this. That's not a thing, nor is that a thing. It's after the 3rd degree, it's a number like that. Jesus.
Literally just like 1 plus 1 plus 2 plus 3. You got it.
Okay, so hopefully you're seeing roughly the same kind of thing where you're getting a new exponent coming down in a factorial.
That's
Yeah?
why I didn't get the factorial.
Okay, so you're getting something like 1 plus, what, 1 x to the first over 1 factorial plus 2 factorial x squared over 2 factorial plus 3 factorial x cubed over 3 factorial. And so more cleanly written.
Why is it over factorial?
That's the Taylor series. All of them are over factorials. All Maclaurens are over factorials.
Oh, I just like
Right.
silly
Okay.
products.
So 1 plus x squared plus x cubed plus x to the n is the general term, or in summation notation starting at 0, x to the n. You could say then that this power series is kind of like what kind of series? It's a geometric series. What's the common ratio?
Depends on what x is.
What's the common ratio? X. So what's the sum of a geometric series?
X1 over 1 minus n. Wait.
Yeah. Okay.
Wait, don't really tell me this.
So that's just one of the 4 ways to get this series. One. Okay. We'll do more. This just. Furthermore, this, it might seem like, who cares? 1 over 1 minus x, that's not even an important function. This is the Abraham of all functions, okay? This is the one that leads to arctangent, to lead you to calculate pi. It is the father of all, okay? So it is a big one. Now let's talk about, what if the center is not 0?
Wait, what do you mean?
If I wanted to estimate, what the heck?
I overshot it.
If I wanted to estimate sine of whatever, sine of 2 with a tangent, what would you pick for your point of tangents? Would you use 0 for sine of 2? What would you use? You can use 2. You don't know sine of 2. Why would you ask me sine of 2? You don't even know. Thank you. Okay. What would you do? What's close to 2? 5 or 2 is pretty close. 1.57, you can do 4, 5, or 3, something like that. Okay, but the point is, you choose a center close to where you want to estimate, so you don't always center at 0. In those cases, then, instead of
Yours is bigger.
f at 0, it's f at c, and f prime at c. It's making the slope match at c, and making the concavity match at c. Furthermore, just like in a tangent line, we say y is equal to f at c plus f at prime at c times x minus c for the point of tangency. Same goes for all the other levels. It's times not x, but times x minus c. So, right? So if we were to do a Taylor series for cosine at a different center of pi over 2, then we would say the Taylor series, now we wouldn't use Maclaurin anymore because Maclaurin means at 0. The Taylor series is, well, first we would do cosine at c, or cosine at pi over 2, which is 0. Then we do the derivative of cosine of pi over 2, which is negative sine of pi over 2, or negative 1 x minus
X.
pi over 2 over 1 factorial, which I'll leave off. Okay, then we go to blah, 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 blah. The next derivative is negative cosine of pi over 2, which is going to be 0. The next derivative is positive sine of pi over 2, x to the, talk to me here, people,
X to the cube.
x to the third, or x minus pi over 2 to the third over 3 factorial and so on, yeah? Now, do you agree that you're getting 0 terms here again because we're using a pi over 2? What if we use pi over 6 or pi over 4? Would you get this dropping out of terms? You would. You would get actually all terms, x to the first, x to the third, and so on, because there would be no zeros there. So that is a possibility. Be aware of it. Now, that's our series. Cool. What's the general term?
Plus X
Is it-
minus pi over 2.
Is it alternating?
Yes.
Negative 1 to the,
N plus 1.
let's always start it at 0, I guess, and so to the
No, that's just the
n,
just to the N.
to the n, yeah?
Because if it's 0.
Starts negative. Okay. X minus
X minus pi over 2.
pi over 2 to the,
Plus.
what's the pattern to the exponent?
2n
2n plus 1 or minus 1?
minus 1 because the first one.
We're starting at 0, so
The first it's minus.
Plus.
Why would it be
plus 1. Because we're starting at 0, when n of 0 goes in, we want that to be positive, yeah?
And
No, that doesn't make any sense because then the second term would be n cubed or x minus pi over 2 cubed.
Isn't that what we want?
Oh, I meant like the. Okay, well.
Yeah, we're skipping over that. Okay, you with me? Over 2n plus 1 factorial. We? Are you with me?
Oh.
Always verify your ideal words.
then
No, no,
the n
because-
plus 1.
Yeah, because you can't. Those don't work the same.
Doesn't it start negative though?
But then
Yeah.
it-
So
Oh, you're right.
next
So it
to
does
it.
need this. You're absolutely right. Sorry. Absolutely right. Thank you. Okay. So that's definitely why you should check every component that makes the first term and it works. All right. Now, if I were to estimate, sorry, this should not be m at 4. This should be t at 4. Oh, no. No. My bad. Okay. Sorry. Cosine of 2 with m at 4 means the Maclaurin we have at the top. All right. Now, what I want to get at is, I could estimate cosine of 2 either with the Maclaurin, which is around 0, or with the Taylor we just made, which is around pi over 2. And then we could compare which one does a better job of estimating, right? So in the Maclaurin, cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. So cosine of 2 could be approximated by 1 minus 2 squared over 2 factorial plus 2 to the 4th over 4 factorial, and they said use M4. Now that 4 does not mean the number of terms. That's a 4th degree Maclaurin. So that means go through the 4th power and stop. Okay? Would you write yourself a note? 4th power, not 4 terms. Not 4 terms. Darn it. We'll finish tomorrow. That should be.
So is this correct?
That's due, you bet.
Well, what about
That's
140?
due. That's the problem.
Yeah,
Yes-
like-
Yesterday's a critique, but make sure you have both tomorrow.
One forty is not due. Well, 140, 180, honorable, 140 is not due. So 140 is
I think that I think she did it.
No, he's
Based off of
so
Yeah, it's not a cluster.
This should be n plus 1 choose n plus 1. Both of these change to n plus 1, not just the x plus 2. I do not. It's
Test you yet?
no, I haven't. Sorry, I looked at them and they're.
Okay, so
I can try and
That's like
post it to my website.
that's the idea behind it.
okay, that would be good. I still want to take my test too.
I will.
I like it.
So I will post it and what it keeps and have a nice day. The review will be posted tonight. I'll try and get it ahead so that you can get it tomorrow as well. If you want it early.
Yeah, we were just about to, but then we were like, we felt bad for the other team trying to give everyone else a chance.
I
Plus, we
appreciate
were like 3.5 people work.
Yeah, some people are smart. It is not. All right. All right. That's done. Hi, maybe. Hello. No, this looks so sweet.
We're already on lesson 140 though. Aren't we gonna finish really soon here?
2 weeks after, probably.
What's your name? What sounds soft to you, Leah?
Just me in general. Like when you insulted my shirt, that's when I was soft. I love my shirt.
Yeah.
What is your shirt? Oh yeah, that's good. I got one yesterday.
So look at my socks.
They also
What?
oh, absolutely. That's fun.
Hello.
You're still thinking.
Did you pick up the set of headphones?
Yeah. Wait. Wait. Is that the side of the bridge?
Yeah, did you pick the set of headphones?
Yeah.
You needed stuff?
Yeah.
Did you get out earlier?
This looks really bad. Why are the bars?
No, Mr. Slaughter told me to distract her. She was like looking at my store. Then Mr. Slaughter was like talking to me for bros.
Not looking forward to this.
What a good sauce.
Yeah, the boxes look really big.
Mr. Slaughter was talking about having like come today. For some reason, he was staring at me.
Why is it twice as big as the normal?
I mean, I guess it is less
I feel like I just became very close to brushing with dad.
Never have you ever given a
Also, what are we doing?
I don't ever.
Would you do number 9 as a warm-up and make it snappy? The lesson is long.
Mr. Kendall and I have to leave at 1:30.
I will almost have you having a clue by then. You'll be this shy of having a clue.
That is what it is.
Yeah. Oh, I'm still recording the last lesson. Come back.